This is an experimental series I'm trying out. I'm trying to see if I can teach all of K through 12 education in 15-minute videos, focusing primarily on science, technology, engineering, and math, but along with a corpus of history, writing, reading, and can't teach art, but I'll try something similar. Anyway, today's lesson will be about physics. And we will solve some problems with me just talking and see if that helps anyone who has those problems in school or hopes to be an engineer someday. First lesson, word problems. Word problems are very annoying to most people. A, because they're unrealistic, and B, they require a lot of reading, and C, they're very different than most mathematical and science problems, in which you're just given an equation or a question and you're expected to give a multiple choice answer, or like 1 plus 1 equals 2, or 5 divided by 2 equals 2.5 or 2.5, etc., etc. I'm minding my time. I have about 13 and a half more minutes. What I want to cover today is how to derive the four kinematic equations. I derive these from scratch every time I do it because I don't memorize equations. In fact, it is effectively unnecessary if you can get the conceptual framework around physics to build an intuition of how the equations do work. We will begin with speed. What is speed? We define speed as the distance traveled divided by time. Now, let's say you are running back and forth on a basketball court. What is your net speed if you end up exactly where you began? It's actually 0. No, correction. Sorry, I have to recap and refresh a little bit of my physics. Speed is just distance divided by time. So your speed would be the total distance you ran. Like, let's say you have 10 meters to run up and down a basketball court. One way is 10 meters. Going from one end to the other end is 10 meters again. And let's say you do that a total of 10 times. Then you have 100 meters you ran. And let's say you did that in I'm not sure what a good estimate is, but let's say you did that in 50 seconds. Then you ran at a speed of 2 meters per second, or if you use stoichiometry, which is another conception which is invaluable to physics, mathematics, and chemistry, 1 meter equals about 3.3 feet. So you ran at a speed of 2 meters, so if you multiply that by 3.3 feet divided by 1 meter, which equals 3.3 meters divided by 1 meter. 3.3 feet divided by 1 meter equals 1, because 3.3 feet equals 1 meter. So you're actually multiplying by 1, which means you get the same answer. And that's how stoichiometry works. We'll go over this and we'll do repetition in more detail in the future. But you run at 2 meters per second, and you multiply that by 3.3 feet divided by 1 meter, then you get 6.6. And whenever you do the units cancellations, and you have on top feet and on bottom second. So you run at a speed of 6.6 meters per second. 6.6 feet per second. Now, there is a difference between speed and velocity. Speed is just how fast you're going in any direction, but velocity has a direction to it. Why does this matter? It matters because of how the physics plays out. A lot of times, you don't care about your total distance. You care about how far you moved overall. There's something called total distance, and there's something called net displacement. Total distance divided by time is speed. Velocity is displacement in a direction divided by time. So let's use the basketball example again. A little trite, but we will continue with it. Let's say that you are running back and forth along the basketball court, and after 5 minutes, you're back where you started. What is your net displacement? One way to do it is to say one direction, the forward direction. Let's say you have point A and point B. Point A is where you begin, point B is where you stop, and you go from A to B to A to B over and over again as much as you can. From A to B, let's say you travel a distance of, let's say plus 10 meters. And because B to A is the opposite of that, it's a displacement along, let's say, a number line that is negative 10. So you go 10 meters forward, 10 meters back, 10 meters forward, 10 meters back, over and over and over again. So we say forward is positive, back is negative. So you could do the calculation and add 10 minus 10, add 10 minus 10 over and over and over again for your total trip. Or you can look at just the fact that all the tens and positive tens and negative tens cancel, and you're left with a net displacement of 0. Displacement doesn't measure the journey. Distance does, but displacement does not. Displacement only starts at a beginning and it measures at the end. It measures a change in a given time frame. It doesn't care about the path. This is actually a very deep physics problem, which I believe Newton and some new scientists like, the Einsteins of the world did grapple with. The invariance of the path. But that has to do with forces, and we're not there yet. We just defined what a velocity was. And since we're just dealing with the math right now, along with some concepts like distance and time, and just took distance or displacement and divided by time, that's where we're at. So we have an equation, which is purely mathematical, for a velocity. Velocity is change in net displacement divided by time. Net displacement divided by time is velocity. So, what's another way to write net displacement? Or, identically, what is another way to write net velocity? Here's the fun part. It's called making identities. This is very invaluable in calculus class where you have to find identities for trigonometry, Pythagorean theorem, tangent, cotangent, etc. This is one of the tools in your toolkit. Finding out what equals what and basically plugging around the equalities very cleverly to get another answer. In fact, there's this theory of math that a lot of the mathematics is just finding equalities. And because there's so many ways to get equalities in math, you get an entire system built. Geometry is like this. Anyway, back to another way to write change in displacement. Let's say you begin at x. Not. X to a subscript of 0, which we call x naught. It's like having an exponent, but instead of at the top, it's a 0 at the bottom of the x. And then x is where you end up at the end, or x final. Let's say x naught is where you begin and x final is where you end. What is your change in displacement? Let's say you begin at 5 feet along the line and you end at 10. Is the 5 x initial or x final? Is the 10 x initial or x final? I will give approximately a 10-minute pause to repeat my question while y'all think about that. X initial and X final. X where you begin and X where you end. Is the X where you begin 5 or 10? If you begin at 5 and you run, if you begin at the 5-meter mark and you run to the 10-meter mark, is the 5 X initial or X final? Is a 10 X initial or X final? Now, X initial, the mathematicians write that as X to the subscript of 0, and X final, they just write as X. And what is the change in displacement? It would happen to be 5 intuitively. So, how did we get that? We did 10 divided by minus 5, of course. So change in displacement in this circumstance is, or it's not change in displacement, it's just net displacement, which is change in displacement is simply equal to the final location minus the initial location. Now, the question is, why is it not the initial location minus the final location? You can write it that way if you want to, but there's something called consistency of nomenclature in science. We have to have a common language. And the signs work out easier if we just say say displacement is X final, the final location minus the initial location along a, say, number line. Now, what is another way to write velocity if displacement equals X final minus X initial? I'll give about 15 seconds for that. While I describe the problem, velocity is equal to displacement divided by time. Displacement equals X final minus X initial if you're traveling in just one direction. This is a simplification, so we're not dealing with 2 dimensions yet. We'll deal with that later. But X final minus X initial is displacement. Velocity equals displacement divided by time. So velocity is also equal to X final minus X initial, all divided by time. This is a very important skill to have if you're ever going to do any mathematics or engineering or science, or even just to have as a day-to-day critical thinking skill. Sometimes one thing will equal another, and that's because there's multiple ways of expressing equalities. Now, let's move on to acceleration, because force equals mass times acceleration, if you remember that memory from physics. I need to do research on why force equals mass times acceleration, but we can define acceleration. Acceleration is a mathematical term. It is something that's a given whenever we're given distance and time. Acceleration is equal to velocity final minus velocity initial, all divided by time. Or acceleration equals change in velocity divided by time. Now, how would you find out the initial velocity of a word problem? Let's get back to the word problems. If you are given acceleration, final velocity, and time, how would you find out your initial velocity in this problem? Remember, A equals V final minus V initial divided by time. A equals V minus V naught divided by T is identical to that. We just changed the label for V initial and V final. And if you know the answer to that first kinematic equation, please put it in the comments, because I have run out of time.